Dijkstra's algorithm is a graph algorithm for finding the shortest path from one node in a graph to all of the other nodes in that same graph. In the last video, we talked about Prim's algorithm, which finds the minimum spanning tree of a graph, which is if you have, say, a village or several villages, what is the shortest amount of road you can build between the villages so that they're all connected. Dijkstra's algorithm is if we already have the roads in place, and in fact, if we have more roads than we strictly need, what is the best set of roads to take in order to get from one village to another, either in the shortest amount of time or in the shortest distance, depending on what is being modelled. So we've got three things here. We've got the graph in the middle. We've got the algorithm button from which is very similar to the other algorithms in this app. And we've got this information over here that my webcam is in the way of. So if I just move myself down to here, we can see this information a bit better. Now, Dijkstra's algorithm is really hard to explain in words, so I think we're just going to jump into a demonstration as quickly as possible, and then we can explain what's going on around it. So we've got this graph here, and like with Prim's algorithm, we need to have a starting point. So, for example, that might be B, and then that will give us the shortest path from B to A, as well as the shortest path from B to C, and B to D. It will give us all of those all at once. So before we start the algorithm, let's just have a quick look at the information here on the right. So this bit at the top above the dashes is a key, and it represents each of these four sections down here. So the bit at the top is the node value. So this is whatever we type into here. So if I type in hello, you can see that this updates what used to be A down here. And if I type in world, you can see that this changes as well. I'm going to take these out, but I'm also going to type in the actual letters because I'm too lazy to think of village names, but also getting rid of the square brackets that signify the default values might make it a bit cleaner. Now these two underneath, we've got wait and previous, which is 99,999 and none. So I'm not even really going to try and explain what these mean for now, because it'll make so much more sense once we actually jump into the algorithm. But I will just say that this 99,999 should technically be infinity, but that can be a bit tricky to represent in computers. You can do it using a bit of abstraction, but 99,999 is sufficient for the Data Structures and Algorithms Visualizer app, because the maximum value of every edge is 9,999. So let's set the starting point of Dijkstra's algorithm to the B and hit start. Now, if I press next, you're going to see that this value over here is going to update. And first thing that's changed is the B has become highlighted, and that means that we have visited B. Now, I'm going to come back to that. The other number here has changed from 99,000, or what should be infinity, to a 0. And what this means is this is the length of the shortest path from the starting point to this node. Now, because B is the starting point, the shortest path from B to B is, well, 0. And because we've now visited B, we leave it highlighted. So now that we've visited B, we have some edges to look at. We need to look at all of the edges from B to the nodes that we haven't yet visited. So in this sense, it's a little bit like Prim's algorithm so far. So we've got the we've got an edge from B to A with a weight of 9, and we've got an edge from B to D with a with a weight of 2. So if I press next again, you can see that these values are going to update. So the shortest path from the starting point to A so far is 9, because we've only looked at these two edges so far, and we have been able to reach A. We don't know that it's going to be the shortest path, but we do know that it's an available path. The B to D is a bit more interesting because we've noted this down as well. We've got a connection from B to D, and because it's the shortest one available, we know that it has to be the shortest path to D. We've started at B. There are only two possible ways that we can go. We can go to D and we can go to A. If we were to go to A, there may be an indirect route to D, which there is. We can go from B up to A, then down to D. But that is guaranteed to be slower than the connection from B to D, because even just getting to A is slower than getting to D. And so because of that, we can say that D, the direct route to D, is going to be the shortest path to D. And that means we can visit it. And if we visited it, then we can highlight it as well. And now we need to look at the connections of the node that we've just visited. So we've got these two extra edges that we now need to check. So the first one here, from D to A, is of weight 5. Now, this is quite interesting because we can now reach A in a different way. We've already got the direct route from B to A, but we can see visually that the path from B to D to A has a weight of 7, which is going to be shorter than the direct route of 9. And so how exactly do we handle this? Because we need to be careful. When we were going from B, we were noting down the actual number of the weight. We were noting down the actual weight as the shortest path to A and D. We've got the 9 and 2, the 9 and the 2. But this time we're going from D, and D is not the starting point of B. D is not the starting point. So even though we can reach A from D with a weight of 5, that doesn't mean that we can reach A from B, the starting point, with a weight of 5. So we need to look at the shortest path to D. We've got this shortest path here, 5, but we need to add the shortest path to D in order to get it. So we can see what this would mean visually. We need to compare the 9 not to the 5, but to 2 plus 5. So we take the shortest path to D, and then we add the new edge to the destination. Because we can reach this in 7, we're going to update this value here. Instead of 9, we're going to have a 7. And now we should talk about what the other value means. The previous is where we came from. So it might be quite useful to know what the shortest path, what the shortest weight from two nodes is. It might be. But that on its own might not, or probably won't be what we want. We probably want the actual path itself. We want to know where to go. And in order to know where to go, we need to keep track of where we've just come from. So the shortest path to D, for example. If we look at the information on the right, we can say we've reached D and we've just come from B. Okay, so if we want to get to D, we need to start from B and then traverse the edge from B to D. And so we look at the previous value for B, and we can see that it says none. Now, if this is all completed, there should only be one previous value left as none, and that should be the starting point. And we'll come back to that in a bit later, so then it will make a bit more sense. But so we've got two paths here. We've mainly been focused on the edge from D to A. We've also got this edge from D to C. Now we haven't reached C yet because there's no path directly from B to C. So this is going to have the infinite value as its current weight because we can't actually reach it. But because the weight of 3 plus the 2 that it took us to get to D, so this weight of 5, because that's going to be less than infinity, then we can update this value here and change the none also to D. And then we need to choose what the shortest path is. What's the shortest path from a visited node to an unvisited node? So B and D have already been visited. A and C have not. So we need a path from either B or D to either A or C. And so we could either pick, and I'm just going to hit next here so that these values update. We could either pick this one, which allows us to get to A from D, and that's now been updated to 7, and we're being told that we need to go from D to be able to achieve this weight of 7. Or we can reach C in a total distance of 5, which also goes from D. Because this is the shortest available, you can see that this is the one that has been selected. And now that we've only just visited C, we also have one more edge to check. We've got this edge here. This is an edge between the node that we've just visited and an unvisited node. So we check this one and say, okay, this is it's an edge of weight 1. And in order to get from the starting point to C, it's going to take us 5 units. And in order to get from C directly to A, it's going to take us 1 unit. So if we go from the starting point to A via C, so we first get to C and then we go to A, that's going to be 5 plus the 1, which is 6. And 6 is less than our current best, so we're going to update this as well. And because this is the only node left, we are going to select this path to traverse next. And now that we've traversed each of the nodes, or in other words, all of the nodes that we have traversed don't have any more edges to new nodes, I think it's easier to think about we've visited all of the nodes. We know that we've finished the algorithm. Even watching it step by step, it can be quite difficult to get a grip of what's going on with Dijkstra's algorithm. So let's look at another example. So let's just finish this up here. And you can see that all of these values reset. And let's just change it ever so slightly. Let's change this 1 to a 3. We're also going to start from B again and see what happens. So the first thing we do is, because we're starting from B, we need to set the shortest path to B to 0, because that's our starting point. We then look at the edges from B, which are towards A and towards D. So we can reach A in 9, we can reach D in 2. Because D is going to be the shorter one, the 2 is going to be the shorter one, we traverse D. Okay, so now we can we've found some more edges to check. Found this one to A, which allows us to get to A in 2 plus 5. And 2 plus 5 is 7, which is less than what we've currently got. So we need to update this to 7 and redirect it towards D. And we can also reach C now for the first time. So we need to update this to 2 plus the 3, which is going to be 5, and redirect the C towards D. So we do that, and we've also selected to traverse C because that's the shortest. And now something slightly different happens. We've just traversed C, and so we've got this new edge to check to get us to A. The weight of this edge is 3, but in order to get from the starting point to C, that has a weight of 5. So in order to get to from the starting point to A via C, it's going to take us 5 plus now 3, which is 8. And 8 is not less than the current best, which is we can reach A in 7 units via D. And because it's not less than, we don't need to update it. In fact, we don't want to update it. We just leave it there, and so we ignore now this edge. And so if we select next, we're actually going to draw the edge from D to A, because this is the shorter path. We've got 2 to 7, or 2 and then 5 to make 7 instead of 2, 3, 3, which would make 8. And now would be a good time to reiterate that Dijkstra's algorithm doesn't find the shortest path between all of the different nodes. It finds the shortest path between any 2 nodes with one set starting point. So we've set the starting point to be A, and we can find the shortest path to A. We set the starting point to B. We can find the shortest path from B to A, the shortest path from B to C, and from B to D. We don't find the shortest path to connect A, B, C, and D starting from B. That's a different problem. Dijkstra's algorithm helps us individually find the shortest path to each other node. If we only care about the shortest path between 2 distinct nodes, Dijkstra's algorithm finds from a starting point to every other node. If we only care about the shortest path to C, for example, what we could do is just when we reach C, we stop the algorithm. We return the value that we want, and we don't need to find the shortest path to A, because it's going to take longer than C. We need to find D first, because that helps us find the shortest path to C. But then anything after that, we don't need, because we've already found what we were looking for. But if we only care about finding shortest path between 2 separate values, we could use a different algorithm, which I'm only going to mention very briefly, and it's called A star. In fact, there are lots of different algorithms you can use, but I'm mentioning A star in particular because A star is a variant of Dijkstra's algorithm. It uses the same kind of idea and then builds off of it. So A star uses a heuristic to choose which edges to check next. It cannot find a shorter path than Dijkstra's algorithm. So for example, we want the shortest path to A. Dijkstra's algorithm already gives it to us. So A star can't find a shorter path. That wouldn't make sense. But it can help us find it quicker, more efficiently. Another thing I should mention is even though A star won't find a shorter path, it can find a slightly different path if the lengths are the same. So if we finish up here and we change this to, I think, A2, we can now reach A from B in two different ways, and both of them are going to have a distance of 7. If we go from B to D, that's 2, D to A is 7, or D to C is 5, and then C to A would make 7. So you've got two different options for the shortest path. Dijkstra's and A star can give a different one, potentially, but only because they are the shortest. They are, or in fact, because they are both the same. If you want to know a bit more about A star and heuristics, I'm going to link a very short video in the description to walk you through it, but that's all we're going to cover for A star now. And I should also say that heuristics aren't always possible, and that's one of the reasons why Dijkstra's algorithm in particular is still really common. So that's been Dijkstra's algorithm, certainly the most difficult algorithm or the most difficult concept in this whole series. But the next video is going to be about depth first search and breadth first search.